All right, well, section 3.3, all that the goal of section 3.3 is basically to take all the stuff that we know about logs and exponents and kind of take them a little bit to the real world. So if you notice that exponents is kind of like a quick rising curve, when you look at the graph for an exponent, it can shoot straight up really, really, really fast. Whereas the graph for log, it's a very slow rising curve. So things you can think of that have exponential growth in the real world are things they talk about, like, cancer cells. It's like you have one cell that splits in two, and then those two split, so then there's four, and then those four split, and it just keeps going and going and going so rapidly. Or if y'all ever saw that movie way back in the day, or if maybe seen it recently, like 28 Days, it's one of my husband's favorite. And in 28 days, and then 28 days later, where this like virus takes over, it's kind of like that. Okay, it just kind of just spreads rapidly, and it's just a goner. Okay, those are things that would have exponential growth. Things that have logarithmic growth, unfortunately, are like savings accounts. Stuff that has money involved with it, because it's just, you're not going to gain that much money. The bank's not going to give away for free. So it's just a very, very slow rising curve. Other things that might have logarithmic growth are really cities. We don't grow that fast. We grow, but we don't grow that fast. And so things like that. And there's even things as, a logarithmic decay. Cities can definitely start dwindling and kind of go down and down and down. So there's some things to think about. But when you're building an exponential equation to model data, the function, here's your main function. This is your foundations that you build off of. Kind of like when you're doing a linear equation, you build off of y equals mx plus b. Well, if you're trying to model exponential, then you build off of this, q of t. So the q means quantity. So the quantity at time t, so after like 5 years, or after 20 days, or after 5 seconds, quantity based on time is going to be, you read that as q naught. Anytime you have a subscript that's 0, you read that as naught. So it's like q naught, which is always the initial quantity present, and then e to the kt. T is obviously your variable, because that's the one in the parentheses over here on the left. And k is just the growth constant. If k is positive, you're growing. If k is negative, you're obviously declining. Okay? So let's look at example 1 in the book. If y'all will pause this video for a second, go grab your book, pull it out, so I don't want to just start working the problem. You have no idea what I'm talking about. So pull out your book, turn to page 177, and let's look at number 1. And after you've done just reading it through one time, let's hit play. We'll come right back to the same point. Okay, so what I did was just kind of write down some foundational stuff. They gave us this main function, q of t equals 400 e to the negative 0.5t. So hopefully you can see it's in that general form of what it needs to be for an exponential equation. And they want us to ask what the growth constant is. Well, the growth constant is always the number attached to your variable in your exponent. So in this case, the growth constant is just 0.05. And if we wanted to convert that to a percentage, remember you just move the decimal 2 spots to the right. So whatever this quantity is, all it says is that t is measured in minutes, so it doesn't really give us much information. But whatever this is, it's growing at a rate of 5% per minute. Okay. What's the initial quantity? Well, the initial quantity is always that base number that's multiplied to your exponential part. So the base quantity is just 400, we can say units. Okay, that's what we're starting with. So from the 400 units, we're building from that at a rate of 5% per minute. Okay, and then in part C, it's just practicing using the function. So if you want to plug in 0 for your exponent, this would be 400 e to the 0.05 times 0, which is 0. Well, e to the 0 is 1, so when time is 0, you have 400 units there. Well, that makes sense, because that's our initial quantity. When time is 0, we should have 400 present. Okay. Then, when you plug in t, it's going to be e to the 0.05 times 10, so that will just make that 0.5. And then you can plug that into your calculator and get some answer. And if you want to, let's practice that, so you can practice using the button. Because what you would do is, in your calculator, you would type 400, then times, you hit second ln, because we're trying to get, and when you do second ln, it kind of sets it up. It looks like this. You're going to do 400 times, when you hit the second ln, your calculator is going to do this. And then all we're going to put in there is, you can either put 0.5, or if you want to do what the function says, so 0.05 and then times 10, either way, you'll get a 659.5. Okay, same thing here, 400 E. Okay, this one is 0.05 times 20, so if you just want to go 0.05 times 20, make sure that's all in one parentheses when you put that in your calculator. And it looks like I get a value roughly of 1087. Okay, so you're getting the idea. The next time you're going to plug in 100 and then so on. Alright, so let's go on to the next example, number 9 in the book. So again, if you guys will pause it for just a second, kind of look at the problem, get an idea, get your feet wet on what it's talking about, and then hit play again, and we'll pick up right back here. Okay, so in this problem, basically they're giving us information on phosphorus 32, P32. It has a half-life of 14.2 days, and then it says if 100 grams of this stuff are present initially, we want to find the amount present after T days. Okay, well, let's take the information that they've given us so far and let's plug it into our equation, our main basic equation. So what we know is the initial amount, so we can say, okay, the amount after so many days is always going to be 100 e to the kt. Okay, so now from that, can we use the fact that the half-life is going to be 14.2 days in order to find what k is? Let's think about that for a second. Okay, so what it's telling us then is that after 14.2 days, so when t equals, when t equals 14.2, so after 14.2, we have half of the amount, because it's our half-life. So then our amount, the quantity, we should say Q of t, should be half. If we say 100, then it should be 50. Or just putting it together into one thing, we should say the quantity present after 14.2 days should be 50 grams. So combining this with the equation that we've already built, okay, so basically when t equals 14.2, we'll have 50 grams. So the quantity is going to be 50 grams when t is 14.2, just like that. Okay, so let's divide by 100. Divide by 100 makes sense. 1/2, because we did the half-life, is equal to e to the 14.2k. Okay, I'm going to come below here to finish solving this out. We're in exponential form. We want to solve for this variable up here in the exponent. So let's take it out of exponential form and put it into log form. The base is e, so let's do the natural log of base e, because the base is e. Go across the equal sign, so the natural log of 1/2 should equal to the exponent, 14.2k. Okay, so let me come down just a little bit further. I want to get rid of the 14.2 off the front. Okay, so if I knock that away, then what I want to do is in my calculator, hit your natural log button. You don't have to do second ln, just hit your natural log button. Take the natural log of 1/2 or 0.5 and then divide that number by 14.2. And I'm basically getting k to equal, if I look at mine, it can be negative 0.049. Let's go with that, round it up a little bit. Okay, now doesn't that make sense? It's that the growth constant k has to be negative? Well, of course, because what we're doing is we're obviously declining, so it's great that it's negative. Okay, so let's take this k value right here that we just found, and let's plug it back into our main equation. So we have right now that Q of t is equal to our initial quantity 100 e, and now we have k. It's negative 0.049 t. So that represents right there our main quantity. No matter what your time t is, that's going to find that for you. Okay, so then so the last part of that problem, what it asks us to find how much is present after 7.1 days. So Q of 7.1 is going to be 100 e, and then again up here, make sure since you're going to be multiplying, you put it all in one big parentheses. So negative 0.049 times 7. Okay. And again, when we're going to use that in our calculator, what you're going to do is you're going to hit 100 and then second ln. So it types in that e to your power for you. Hit negative 0.049 and then times 7. And then when I do this, what comes out is roughly 70.9. Let's just do 71 grams. Okay, and there's the answer for the second part. All right, let's go to the last problem.